NetApp's implementation flow. Metrical app, REST API, having REST API, it is connected to NetApp, that is, this is a container, in this container having REST API, NetApp, here this is file code. Here first one is request to NetApp. 2.1 make request to 5G API code. 2.2 get reply. 3 NetApp reply. Asynchronous post notifications to callback endpoint. Callback here. This is the callback. NetApp. From this NetApp connected asynchronous reply to vertical app. Dual flow. In and out is there. Here only NetApp going to REST API. One flow, single flow only. One way only. Here also dual, two-way. Some implementations of NetApp there. NetApp as it is the case in consider an external management function NetApp controller to which the NetApp delegate the interaction with the 5G APIs, 5G APIs. With this approach, NetApps can be defined as cloud-native microservice applications composed of multiple NetApp components that interface with the 5G control plane through a common NetApp controller. The decomposition of NetApps into microservices allows the NetApp controller to manage the placement of each component, acting also as a MEC orchestrator. In this case, NetApp developers shall also provide a descriptor with the recorded traffic characteristics for the data plane communications into each of the NetApp components. Based on that, the NetApp controller can be charged. NetApp controller can be in charge of managing the life cycle of its native components, ensuring that the record service level update are met by triggering offloading of traffic between NetApp components deployed centrally or at the edge in figure 2.21. NetApp deployment over a 5G network using NetApp controller. So here this is other application, external access, NetApp. NetApp having VNF running on cloud, module Y, VNF running on edge. So module Y connected to mod X, module X in a VNF running on edge, and then this module Y connected to other application, external access module Y connected to other. Then 5G up UPF cloud, this user plane, NGFW NFVI. This UPI edge also connected to Model X, UPS Cloud and the RAN. RAN also connected to NetApp client UAV and then connected to 5GCP. This is core NFVI. This is user plane. No, this full user plane. Okay, edge NFVI. So NetApp controller and MEC orchestrated traffic control rules API connected in between 5GCP and NetApp controller and MEC orchestrated. 5GCP having PCF, NEF, SMF, AMF. So here this is the control panel. In this control panel having UPF Cloud, VPF Edge, RAN, Edge NFVI, user plane, core NFVI, VNF running on cloud, Model Y, Model X, VNF running on Edge, other applications, external access. So this is a NetApp deployment over a 5G network using NetApp controller. Integration of 5G RAN with unmanned aerial systems, UAS infrastructure. U for unmanned, A for aerial, S for systems. So applications of unmanned aerial vehicles including flying drones has been initiated in a wide range of civilian and commercial activities areas such as cargo delivery, precision agriculture, remote inspection, photogrammetry, video streaming, rescue and search, and data collection for the Internet of Things IoT. The C2 command and control link of a UAV establishes communication between UAV and the ground control station GCS or other ground systems, such as the radio controller. It must support highly reliable, low latency and secure two-way communications. We are seeing two-way communications, usually with low data rate requirement. Usually with low data rate requirement, so that the critical command information between the UAV flight controller and the ground control stations can be effectively exchanged. On the other hand, the payload communication link is used for transmitting data applications and usually supports high data rates, thus requiring high throughput. The type of data may include image, video, relaying, or backhauling data packets. heavy LIDA or data in LAS format. The integration of 5G network into the UAS infrastructure proves to be a vital for in achieving the success criteria and the KPI required along with the quality of service as defined by 3GPP, GSMA and the other requirements. Architecture integrating 5G infrastructure with the U-Space. This is U-Space here with dashed line. Dashed. This is the U-Space. Architecture integrating 5G infrastructure with the U-Space. So U-Space having 5G infrastructure, 5G infrastructure having data link, and then it is connected to 5G network owner, and again connected to deployment module. OSS plus VSS. So here also this color pre-deployment step 1, next one color, this one color, this one pre-employment step 2, post-deployment, this one control mode, post-deployment, and then post-deployment red data here in a 5G infrastructure. So you use this service provider 8 to B2B, USA traffic management, controller module, planning, deployment schedule, business provider, end user, B2C, B2B. As part of ongoing trials in 2239, the project has modified version of the trial architecture as shown in figure 2.23. UAV trial architecture 2239. Authorities connected to UAV traffic management, web portal, 5G facility, trial owner. This was 5G trial engine. It has trial scenario, validation, blueprint, KPI list, preparation, validation, deployment, result analysis. Web portal connected to preparation and validation, deployment and results, and trial owner UAV vertical. This 5G trial engine connected to web portal, UAV traffic management, 5G facility, and care validation in between the 5G facility in preparation validation. Care network slice facility template towards 5G facility. KPI results from 5G facility to result analysis. Then UAV traffic management, two-way C2 link, and the UAV traffic management. Authorities and UAV traffic management, two-way. 5G facility provides of 5G infrastructure to trial UAV use cases, including computation capabilities in the form of edge cloud or centralized cloud resources, and 5G connectivity in standalone mode and non-standalone mode. All the facilities include 5G NR base stations, support network slicing. Third one, manage the life cycle management LCM of VNFS. The 5G facilitator play the role of the 5G infrastructure in the reference architecture. Public-private network interoperation. Public-private network interoperation in this 2.7 table. Architectural solution 5G PP project, additional reference. Architectural solution is public-private network interoperation. 5G PP project, 5G in additional reference 2231. The system demonstrated in 2.31 can be facilitated for ENI NPN provisioning, where the experimentation facility is taking the role of ELMN and the vertical provider sites, example private sites like industry 4.0, factories, campus, transportation hubs, etc. Are taking the role of